Hi, my name's Tom, and today I'm excited to present my final project for robotic manipulation on augmenting ICP using dense object nets with applications in surgical robot perception. State-of-the-art robots for vascular surgery offer minimal autonomy. Surgeons maintain direct control over wire-based surgical manipulators, and many surgeons are deterred by the associated learning curve. A major obstacle to higher autonomy surgical manipulators is developing highly robust simultaneous localization and mapping. Ultrasound is the primary imaging modality utilized, and we are interested in developing a SLAM algorithm capable of mapping an unknown vessel geometry in vivo. ICP is a common front-end algorithm used in acoustically based SLAM. However, as we learnt in class, ICP is susceptible to convergence to local minima in the case of poor initialization or minimal point cloud saliency. Intraoperative ultrasound suffers from both these issues, though exploitation of 3D priors from preoperative imaging has the potential to improve ICP performance. Therefore, I propose the use of contrastive correspondence learning between adjacent depth images simulated from a prior CT mesh. These correspondences will be used to inform registration tasks on real ultrasound point clouds representing successive poses of the robot. Prior to intervention, the surgeon would run the following data generation pipeline. First, we select a random pose inside the preoperative CT scan to represent the surgical end effector and generate an offset pose to simulate motion of the optical frame. We utilize a combination of raycasting and an inverse pinhole model to generate simulated depth images and ground truth pixel-wise correspondences. This dataset is then fed to a dense object network, which is a similar framework to what we learnt about in class. Finally, we calculate pixel-wise loss in the descriptor space, given knowledge of ground truth correspondences. To illustrate quantitative results, first I show the pixel-wise correspondence precision. The network did not perform as well as the original architecture proposed by Florence, likely because we were working with sparser depth images in comparison to rich RGB information. It was noticed that when the probe views surfaces from far away, interesting structures like vessel subbranches and significant variations in curvature are evident from depth images. Therefore, in future work, it may be possible to apply a larger weighting to high-intensity depth values in the pixel-wise loss function. Here I demonstrate the registration performance for vanilla ICP and network augmented ICP across 40 point cloud pairs. Dawn ICP had a lower inlier error average. The variations were not found to be statistically significant. To explore underlying factors for this, I'll now discuss some qualitative registration results. Pictured here are two sets of sample images where ICP failed completely and Dawn and ICP did not. Qualitatively, we see that ICP converges to a local minimum, though it appears that the Dawn provides a good enough global initialization for ICP to converge. Dawn and ICP found a valid solution in 6 out of 40 point cloud pairs, where ICP failed completely. Future work will look to address the sim to real gap by implementing noise models in the data generation pipeline. Thank you.